Garvey. Welcome to Saturday Matters. I'm your hostess, Karen Place, and I have had the pleasure of introducing Jerry Garvey several times. So go ahead, let's get our brains bent.
Okay, good morning. If you'll indulge me for a few moments, I'd like to offer thanks to a variety of people who've been so helpful. First, Karen, thank you for providing me with the opportunity to give this talk, and I want to thank Will and Anders down the back for getting me here and getting this whole thing set up so that I can proceed. And first, greatest of all thanks to my wonderful and beautiful wife, who of 65 years, she is pushing herself to the limits to see that my wants and cares are looked after. Our children have been absolutely wonderful and supportive. Thank you, Deirdre, Gerald, and Tori. A granddaughter, Cameron, is actually here today, and thanks so much, Cam. Thanks also to many of the students and colleagues who have emailed me just the very kindest emails you could imagine. I'd like also to thank Don McMillan and Paul Spitzer, who are trying to keep getting the UHU, that's University House University, seminars restarted again, and please support their efforts. Thanks also to Tom Gormley for that beautiful craftsmanship that he did on that blade of change that's out in the garden at this moment. It's a marvelous job that he did and so kindly dedicated it to me. And thank you all, residents and staff. Living here at University House has been stimulating and pleasurable, and you've all been such an important part of it. Thank you. So let me now get on with the business of today's talk. I'm going to talk to you about time, which when I turned to it, I learned a great deal that I hadn't known at all. This little thing that's on the screen up above is an optical lattice. It's a way of holding atoms in electromagnetic fields so that they're shielded from one another, but you can group them together so you can have the benefits of getting the radiation from a whole bunch of them with minimal interactions between them. So the outline of the talk I'm going to give is give you a bit of history, talk about time and periodic phenomena, navigation in time, and going from clocks to GPS, the global positioning system. Electronics, counting cycles, and I'll define the definition of a second. Counting faster turns out to be incredibly important, and you have to involve things like frequency combs, new atomic standards, and optical standards. I'll talk about a bit about the measurement of gravity and a possible the possibility of using nuclei as the future standard for timing. So recently there's been several major advances in being able to accurately measure time and make use of that fact. Today, I want to acquaint you with some of those, and we can marvel at the technology that just keeps getting better and better as time goes by. It's been growing so rapidly, in fact, that it currently outstrips our ability to know what to do with it. It has increased, believe it or not, 15 orders of magnitude over our lifetime. Time is a scientific unit that can be measured with the greatest precision. And that's because it simply involves counting. If there's anything that physicists are good at, it's counting. The mastery of classical electromagnetism coupled with electronic digital technology and atomic physics greatly advanced our capability to measure time. Most of these developments have occurred after World War II and continue into the present. Given where measurements stand today, I was amazed to discover that as recently as World War II, the best timekeeping devices were mechanical. During World War II, the most accurate clocks were marine chronometers, particularly those produced by the Hamilton Watch Company. They were considered the finest ever made. These high-grade, spring-driven timepieces were used for precise navigation and were the best available for timekeeping accuracy by the U.S. military. What was so surprising is that there had been little to no improvement in the ability to measure time over the previous 200 years, beyond what a man by the name of John Harrison, who made a wooden clock in England, had achieved. In the year 1761 to 1762, one of his clocks is claimed to have lost only 5 seconds over 81 days. That's pretty amazing. And he won a 20,000-pound prize, the current value about 1.7 million pounds, the clocks and the maps that the clocks allowed you to make played a large role in England's mastery of the oceans. Here's a picture of Harrison's first clock. This wasn't a prize winner. This baby was 4 feet, 4 feet tall, and the timing was driven by these 2 pendulas coupled by this spring that had them going boing, 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 and that's what was keeping time. And we didn't do any better than that for 200 years. Keeping track of time normally requires counting the number of times that some periodic phenomena, that is, something that keeps happening over and over again. For example, the number of times the Earth has gone around the sun gives you years. The number of times the moon has gone around the Earth, it's approximately months. And the number of times the Earth has turned on its revolution, it gives you a count of the number of days. Well, how are you to break a day down? Sundials are not bad, but they obviously change as you change your location on the Earth. Pendulums are kind of a natural way, but my gosh, you know, the pendulum is a man-made creation, and besides, if you're going to take it on a ship that's going to end up rocking at sea, it's not a very natural timekeeping device to keep along with you. So moving oscillating systems driven by a spring were devised and constructed by John Harrison and others, and developed to meet the needs of navigating the oceans. Time proved essential in establishing where you were when you were out of sight of land. So the way you could tell what your longitude was, that is how far from the North Pole you were, was you would be out at sea, you sighted the horizon with your sextant, and then pointed the other angle up to tell you where the North Star was. And that angle between those two things, the horizon and the looking at the North Star, told you where you were relative to being in this position. Longitudinally, the next thing you needed to measure was how far you were moving in an east-west direction. And the key to that turned out to be time. So if you had a clock, let's be English for a moment, and you had the clock set up at the observatory in Greenwich, England, and you started your voyage in time with that clock, and you then set sail. The amount that you had traveled could be measured by determining when the sun was directly overhead. That told you how far the Earth had rotated so that the sun was now directly overhead. And on board, you had a clock that told you what the time at Greenwich was. And so knowing the difference between those two times, you could tell how far you had gone in an east-west direction, which was, of course, a combination of your sailing plus the rotation of the Earth, which you were able to figure out. Now, the commercial world seemed okay with that kind of arrangement, and actually after World War II, they were still using it until September the 1st in 1983, when a Korean Airlines flight called FL 007 leaving Nome and trying to fly to Seoul, South Korea, actually lost its way due to a navigational error and ended up over Soviet airspace. The Soviets shot the plane down, killing all 269 people on board. 2 weeks after that, President Reagan made a limited version of the United States GPS system available to the commercial world. It was a project that had begun about 10 years previous, and its roots were in a series of satellites that were going to be flying around, whose position you precisely knew and you could communicate with. So Reagan made available a limited version of the capability of that thing. It was nowhere near as good as what the military had at their disposal at that time. The World War II had allowed for many advances in electromagnetic technology, radar, computers, the manufacture of transistors, and so forth. And it had gone along well enough that in 19 1967, the international units, system of units had adopted the inverse second. So finally, we had a really good definition of what a second was. It was going to be 9,192,631,707,70 oscillations of the cesium 133 atom. The first prototype of the thing had just been launched in 1978, and the full constellation wasn't really completed until 1993. So allow me to digress then for a few moments on the GPS system and how it works, as precise timing is very much at its center. And we don't really appreciate the role of precision timing that's come to play in our lives. You know, how does everything know exactly where we are all the time? It's they're just keeping track of us, and the precision in timing and communication has made that possible. So when you accepted this new standard for a second, the velocity of light was then defined to be this distance. That's how many meters it would be traveled in a second by a light wave in vacuum. And thus the meter became the distance traveled by that. I'm not going to go through reading that number again. Cycles of the cesium transition. This new definition of a second changed the precision in timing from something like a part in 10 to the 5th to a part in 10 to the 10th, and it based it on an unchanging universal harmonic transition. That is, every cesium atom would behave in exactly the same way, and so you now had a standard that you had not set, but that nature had provided you with, and you were making good use of it. So this upper figure here on the right is supposed to, in some very poor way, show you one of the outermost electrons in cesium just flipping its spin. So the electron was pointed in one direction, and you just turn it around and flip it over. The way you would make a machine that could provide you with the radiation you needed was you would have an oven with cesium in it, heat it up. The stuff would come out of the oven mostly in the ground state with its spin down. You would select those atoms that had their spin in the up direction, put them into a resonant cavity, and they eventually ended up loading that cavity with radiation and becoming a laser source for that frequency of light. So it would be great if you could, it's a pretty low energy transition, and using more energetic transitions would allow you to make an even better determination of time. But if you were going to do that, you'd have to find a way to be able to count those big numbers. And that ability to count let's see, 9 trillion No, that's trillion. 9,192,631,770 cycles was the limit you could do with the available electronics. So you had to find some new way to do it, and by gum, they did. But first, let's say a few words about the GPS system. So there are ideally something like 24 satellites whose position we know very well. So they're about 20,000 kilometers, 16,000 miles above the surface of the Earth, circulating regularly. They make a revolution around the Earth every half day. You see, that's roughly 12 hours. That's in the height in kilometers. And at any time, something like 5 to 8 satellites would be visible from any point on the surface of the Earth. So, here we are again, stuck with our problem of trying to establish where on the surface of the Earth we are. And what happens is you have a GPS receiver. You send out a signal and the satellite pick up the signal from, let's say, 4 satellites, A, B, C, and D. And that determines 4 equations that allow you to determine the position of the receiver. The position of the satellites are known, so you know where satellite A, B, C, and D are. And on board, it has a very accurate timing interval. It receives your signal and knows the time that it took for that signal to get from where you launched it to the satellite, and they broadcast that back to your receiver. So they tell you just how long it took. So you know the time that it took for the signal to get from each one of those satellites to your receiver. That uniquely establishes how far away those 4 things are, and they have sent out broadcast out circular signals from their satellites. So their common intersection of those 4 signals gave you a chance to know exactly where you were on the surface of the Earth. The atomic clock was stable enough to maintain 1 second in 300 million years. So that's about a part in 10 to the 14th. To be really useful, a relative timing signal has to be less than something like 10 to the minus 9 seconds. And that would allow you to establish where you are to 1/3 of a meter. If you work on it really hard, they claim that with the GPS system, you can localize where something is to 2 centimeters. It requires correction for atmospheric effects, and most of the software necessary to do that is secret and in the hands of the military. So these magnetic transitions, like the ones that happen in cesium and hydrogen, have a low enough frequency that you can directly count the number of cycles that they know that they have in a second. As soon as you go to atomic transitions, however, that is, you excite an electron from one orbit to another, much higher energy is involved, and hence higher frequency is required. And then you had to find out some way of extending counting that you had to uncover and end up developing. And so here was hydrogen, and it had an energy of, here it is, 5.87 micro electron volts. And so you'd like to use an atomic thing, and you would go to say something like ytterbium, which had a transition of 2.85 electron volts, almost 1,000,000 times higher in energy, and hence the frequency rate would be 1,000,000 times faster. And there's no way you knew basically how to count them. Similarly, there was a wonderful use of strontium with an energy of 1.78 electron volts used as a standard. So in order to establish this ever finer base of higher frequency, you had to figure out how to do it, how to count it. And the best that electronics could do is count basically billions of cycles per second. And this dilemma was really solved by a Nobel Prize winning invention and application called optical frequency combs, that takes a much higher optical transition frequency and breaks it down into multiples of countable radio frequencies. So the frequency that you were looking for was an integer multiple of the known thing, like cesium, that you would use, times a small offset called the carrier envelope offset. And you could actually then get this much higher frequency in terms of hundreds, thousands, or millions of times the previously established standard. And so that meant that you could move from just radio frequencies. That is, this is the entire spectrum of electromagnetic radiation that I'm showing, from a frequency of something like 1,000,000 cycles per second to something like 10 to the 20th cycles per second. Here's where the little bit of that spectrum that we humans can see with our eyes, this little sliver out here where we see the different colors centered on yellow, because that's the dominant thing that the sunlight comes through with. So we were able then to make use of frequencies that went basically all the way from microwaves through the infrared into the ultraviolet by using the idea of frequency combs. And this number n would be easily as large as can be easily as large as 1,000,000. And so a whole big piece of the electromagnetic spectrum had become countable. So we were able then to tie radio microwaves, and optics all together in a very, very quantitative fashion. There were a large number of atomic transitions became secondary standards. Here I show them, and their various relation to that original cesium source. Everything was eventually tied back to that. Here was their working frequency, and this was the variation in frequency, delta F, small change relative to the frequency itself that you could be sensitive to. So the terbium clocks and strontium really were vast advances over what one had been able to do with cesium, which originally had been a part in 10 to the 10th. It was now, had improved itself so that it was a part in 10 to the 13th. So how many seconds have gone by since the Big Bang? Well, the Big Bang was 14 billion years ago, and here's the 14 billion years. This is the number of seconds, 3.15 times 10 to the 7th seconds in a year. So there have been 10 to the 17th seconds, 4.4 times 10 to the 17 seconds, roughly, since the Big Bang began. And here you are with a sensitivity that is greater than that. So you now have clocks that if you started them when the Big Bang occurred, they'd still be accurate to within 100th of a second. Fantastic. From where we were when we were born. What an incredible thing. So one use of this was to investigate a prediction of Einstein's theory of general relativity that talked about the gravitational effect on frequency. And what Einstein had predicted that if there were a change in frequency, let's see, where are I? But at any rate, these guys in their experiment, which they used as strontium clock as the absolute measure, they were able to reduce the uncertainty to a factor of 7.6 times 10 to the minus 21. It makes a whole new regime of clock operation possible, and it makes it incredibly important that you keep track of how high the clock is. Because as I'll show you, they can show you a frequency shift that takes place in a millimeter change in the elevation above whatever is the Earth's gravity at its surface. In order to do that, they had to take about 100,000 strontium-87 atoms and make them very cold. This is just slightly above absolute zero, and load them into a large shallow waist optical lattice. So that optical lattice, let me see if I can run back there quickly. Yeah. So here are the atoms trapped in the optical lattice. And this optical lattice is set up by setting up electromagnetic fields with lasers that are shining on one another, and their interference sets up this electromagnetic potential. And you can vary this potential. It's quite shallow to start with, but you can make it even shallower and get almost a field-free environment for the radiation from this particular atom, and isolating it from any of the effects of the other atoms, and that allows you to get a sharper and sharper line. Oops. So here was this setup they had. They trapped the atoms in one of these optical lattices. These two mirrors were about 15 centimeters apart. They could shine light in to get the resonant frequency out of about 15 of these little trapped regions. There was a magnetic field that was held in this, that was coming in this direction, and of course gravity was in this direction. So the elevation is increasing as you move up this lattice. They went ahead and measured the rate of change of that frequency as you go up the lattice, and sure enough, they ended up verifying Einstein. Einstein would have predicted that this thing would have been 1.109 times 10 to the minus 19, and here we are just, there's the prediction shown here, and these are the measurements as well as they could make them, and if you make a straight line approximation, you got a number that was in very good agreement with what Einstein predicted. This is the dates of when the various measurements were made. So now you have to pay incredible attention to height if you're going to be making a very sensitive measurement. And these guys had gotten themselves down where if you move a millimeter, you have changed the fraction of the frequency apart in 10 to the 19th. And you can measure it. But these crazy people who do this stuff just don't give up. They wanted to do even better. And the only way you could actually do better is to end up trying to isolate the system even more. So what they did was look for a nucleus that might have a low enough energy that you could make use of it as a time standard. And lo and behold, if you just searched most of the lowest excitations in nuclear isomers were the order of 10 kilovolts to a million electron volts to an MeV. But there was one crazy thing, thorium-229, that had an excitation level that was only 8.2 electron volts above the ground state. Very, very unusual thing. You can see removed by something like five orders of magnitude from the typical typical excitations. And so the way you would access this thing is you would take and with two lasers shine enough light so that you excited the electrons in thorium-229, and they would transfer their excitation to this isomeric level at about 8 electron volts, and you could then hang around and sense its decay and actually end up measuring it. So thorium, this nucleus 229, is not found in nature. It comes basically. This turns out to be incorrect. It is not from the alpha decay of plutonium, of uranium-233, misprint. It actually is made in reactors. It had been known that there was this low-lying excitation for about 40 years, but only recently did they find out what it actually was, and not only did they find out what it actually was, they've ended up measuring its frequency very, very precisely. They did this by putting the thorium into a calcium fluoride crystal and exciting it there with a known laser with radiation from strontium, which you recall was a thing that we had made as a secondary standard. And it turns out that about the 7th harmonic of the radiation from strontium was ideal for making a match to the frequency in thorium. So now you have a new potential frequency standard in a thing that is really shielded, because it's in the nucleus, which is at the center of the shield of electrons that surround thorium, that it's much less going to be affected by its environment. And so without any effort at all, they achieved a frequency 10 to the minus 13 in getting this job done. But they're going to focus in the future all their attention on reducing the effects that broaden this line and getting the frequency down to something like a part in 10 to the minus 21. And as I say here, Lord knows what you'll be able to do with it. But they're just having such a good time of measuring frequencies more and more accurately that there's apparently no end in sight. So thank you.
Thank you, Jerry. Anyone have a comment or question? No. Do you want to do the microphone, Lorene? Okay, it's yours.
Well, I mean, I think that's what's so fascinating about this. This is so outside what we know how to make use of, that the next breakthrough that comes from where we realize where we could do what we could do with this will be, I think, quite significant. I have no idea what it will be. I don't think it will have anything to do with positioning. It may have a great deal to do with the speed of which you can access memory, how big the cloud could get.
Oh.
Yeah, because now you can end up interleaving things in much tighter timing than you could before, and carry all that much more information. Because in a sense, every cycle is a piece of information. And now you can assess all these pieces of information much, much faster than you ever could before. In fact, so fast, you have no idea what the devil to do with it.
Your appearance today is delightful, and a reminder of how much we've missed you and your contributions, both intellectual and cultural, to the community here. My question is both related and off subject. We're about to elect a president, one of the candidates of which is adverse to scientific activity. For example, he would imprison Dr. Fauci for his scientific contributions. Once upon a time, you were a little sanguine about the outcome of the election, and I'm wondering what your current feelings are about what will happen next Tuesday.
Thank you for the kind words, and for some reason, I just remain perhaps hopelessly optimistic that this country could in no way elect Mr. Trump as its next president. One reason that he doesn't like science is, he just doesn't like facts, and things like I'm talking about here, where the nature of the science is quantitative. That man has no real sense of quantity at all, because it is the clearest way of revealing whether something is, true or not. 2 plus 3 is not 6, or maybe some number less than 7. We actually know what it is, but Mr. Trump doesn't. and I think the requirements that science puts on you to be accurate and correct are the kind of thing that Mr. Trump finds so difficult to deal with.
Don, yes. Thank you, Gary, for a tremendous amount of work that you've done today. All the slides and the pictures and so on. I know a lot goes into this. I've got one basic question. Going back to that very first 4-foot device that an Englishman built.
Yeah.
How did he decide really what 1 second is, and why do we have 60 seconds to define a minute, and 60 minutes an hour, and 24 hours a day? How did that come about?
Apparently it goes way back in history, Helmut. The number 60 was really valued by the ancients because it was divisible by so many things. 12, 10, 5, 6, 2, 3, so and even 4. So you 60 had, because of its being broken up so many ways was a great feature, and so that seems to have been the beginning of the acceptance of 60 as a number that would end up playing an important role. I don't know if I satisfactorily answered.
Well, going back to that wooden device.
Oh, yes.
The oscillation time in there, is that something that just came about because...
That was set up so that the oscillation time was just about a second. It was a natural frequency. There was a pair of pendulums, inverted pendulums, coupled by a spring, and their natural time frequency was very nearly a second. I don't recall exactly what it was. What I showed you was a clock that is referred to as H1. It didn't win the prize. He had to go through 4. So H4 was what won the prize. And unfortunately, H1 looks just like a big pocket watch. So if you take a picture of it, it doesn't tell you anything. I thought it was revealing to see the guts of a thing that could keep time, made mostly of wood. Yeah.
This goes more to something practical. You said that a GPS receiver sends a signal to the satellite.
Yes.
That kind of boggles my mind that you might have 100 receivers all sending signals and satellites responding to each of those.
Sure. That's where all this marvelous timing is involved in. It just knows it's received a certain signal at a certain time. It has registered that reception time, and the signal that you sent carried in it the time that you sent the signal. And so it's there is some, as you might imagine, some logic going on in both the receiver and in the satellite.
Thanks. You talked about the time correction due to general relativity, the altitude. There's also should be a correction due to the special relativity because those satellites are moving. How much of a role does that play?
Let me see. I think the effect of gravity is one of the largest things, Henry, and that's something like 6 cycles out of that, roughly 10 to the 10th that were there, and the transverse Doppler effect is again calculable. Both of those corrections are made in actually.
Sure. I just wondered how big it was compared to.
Yeah, I know, yeah. And I'm afraid I've forgotten the number other than the correction due to gravity. Yeah.
Simple question. About the satellites, because they're man-made or man-positioned, are they subject to slowing down or deteriorating, and what happens if they change?
Well, we're in continual contact with those satellites. There is a master timer that I think there are, 4 other GPS systems up there. One run by China, one by Russia, and an English one. They all agree on a fundamental base for what the absolute time actually is, and so there is agreement as to what the time is. And they keep broadcasting basically every second or so to their satellites what that basic time is. So even though these clocks are incredibly precise, they are also being updated every second to just keep them on track. Yeah. So we continually replace the satellites. Some are probably not taken down; they're just turned off, and you send up another one. It takes a little while to establish exactly where it is in the sky, and getting its position accurately enough so that it becomes useful is important. And that once that job is done, it's then part of the gang.
My question has to do not with content. I did not understand enough to ask a question about the content, but more has to do with your motivation and your decision-making process as you pick these topics to present to us. When I first was moving in not that long ago, you were doing a series on cells, I think.
Yes.
And then you did a series on artificial intelligence. And now this. What is it that drives your decision?
But what was the question?
What is it that drives your decision about what to present to us? How to pick the topics?
Okay, so part of it is I want to do something that is not just useful for you, but it's useful for me. And what I was shocked by that led me to do this was to find out that as recently as World War II, we were still using mechanical clock to be the basis of time. And over our lifetime, we have increased our sensitivity by 15 orders of magnitude as to the elements how finely we can measure time. So it was that shock that, oh my God, look at how fast things have changed. And it's really, in a way, a part of a general feeling that I have is so much is happening so fast in so many fields that we're becoming overwhelmed by everything that we everything that we are learning. I don't know what we're going to do with it.
Add a little something to that. I know how Jerry chose at least one of his topics. It was in a conversation with my wife, Betsy. And she was wondering about unemployment and that kind of thing. And her question provoked Jerry's interest in labor dynamics. So the next thing you know, he's in here on a Saturday giving us, the population and, and that sort of thing. Other things he's done just in the time I've been here, about 5 years. I've only been here about 3 days when he did something on viruses. He and Lester Goldstein together. He just got into, he read an article in a science magazine about viruses, and he thought, this is really very interesting, so off he went with it. He's done cryptocurrencies, all of us get interested in something, but Jerry actually goes ahead and swats up on it, and the next thing you know, we're all here on a Saturday.
Yes. I think it's very easy being a physicist. We just are interested in quantitative things. And Betsy's question about where have all the workers gone, I think by her asking the question, and I might have gotten to the answer sooner than almost anywhere that I've read, that the slow realization that what had happened was it was baby boomers. And the baby boomers were now, who had supplied all the work that was being done, were now moving into the people who you had to look after. And they were moving out of the labor market. And it was quite clear that when you looked at the numbers, that was the answer. And that was a great question. Betsy, thank you.
I think I embarrassed you once when I introduced you as one of our resident Renaissance men. But it's definitely true, isn't it? Any more? One more? We're okay, Don, and we're over time, so after this.
Malware has destroyed things like the public library system here. How vulnerable is all of this time stuff to malware?
Boy, I would think these guys, the people, the small cadre of people who are at the forefront of developing this stuff are so far ahead of everybody else. I don't think anybody can touch them.
But the Russians have blown satellites up.
Oh, well, they did that first, but
Crude old-fashioned way. Thank you all for coming, and especially thanks to Jim.